Okay, good morning, everybody, and welcome to our iDROSET, the new generation in static balancing webinar. I'm your host, Greg Jackman, the specification program specialist here at Watts. Just to give you guys a little bit of a background on our webinars, we hold several of them throughout the year that cover a variety of topics. Our presenters are always our in-house technology and product experts. And today's webinar is geared specifically for you guys, our contractor customers. We'll be discussing different types of balancing valves, the typical circuit setter balancing process, and how to speed up that process without sacrificing flow set accuracy. So now I'd like to introduce you to the presenter of today's webinar, Jim Earhart, our hydronic product specialist at Watts. Jim has over 40 years of diverse experience in the hydronic industry. He began in product management at Watts in 2007, leading the development of patented new products, including the ASMB air separator, RBFF service valve, and the TWH Gen 2 tankless water heater service valves. Jim is also an experienced trainer and a certified instructor for the ASSE 19210 Hydronics Heating and Cooling Installer Certification course. So we wanted to have a little fun today and do a giveaway with you guys. So throughout today's webinar, we'll be giving away not one, not two, not three, but 4 Watts portable tailgate coolers. You know, you can take it to the beach, a sporting event, use it in your backyard. It holds up to 50 cans, and it's designed with a removable lid, so everything doesn't spill out of it, and it keeps the bugs out of it as well. So the way this giveaway is going to work is that we're going to have 4 quiz questions, each scattered throughout the PowerPoint presentation today. And so when a slide pops up with that quiz question, if you're the first person to submit the correct answer in the chat window in the WebEx, then you'll win a cooler. So we'll be doing this 4 times throughout the webinar, but you can only win once, just to get that straight. You know, just the questions will come up quick and without much warning, so just make sure you're paying attention. And here's a screenshot of how to submit a chat question. So during the duration of Jim's presentation, all your phone lines will be muted, but we definitely encourage you to submit questions via the chat window. You just hover over the chat icon at the bottom of the WebEx there, and you can type it in there. We'll then address them as we go along in the presentation and then afterwards as well. And of course, this is where you'll be submitting your answers to each of those quiz questions to try to win a cooler. So with all that said, let me pass it off to Jim to get started.
Thank you, Greg. Good morning, everyone. Thank you for joining us for this morning's session. As Greg mentioned, this is on our new iDROSET static balancing valve. We'll be discussing the valve, how it's going to help you on the job, get out quicker, make more money on the job, etc. The quizzes should be fun. Be ready when the slides come up. Be ready for your answers. Get one of those coolers. They look mighty good to me. Part of our agenda today, we're going to be looking at why we need to balance a hydronic system, whether that's a heating system or a cooling system. Kind of a 30,000-foot view on how we do that. We're going to talk about the ideal solution for static balancing. And then finally, we will talk about the technical features of the new iDROSET valve. So with that, we'll get the program rolling. So why do we need to balance a system? And this all starts really for a typical commercial application. It is going to start with the specifying engineer. And if you look on the bottom left of the screen, you'll see an equation that reads GPM, gallons per minute, equals BTUs per hour over delta T times 500. So the gallons per minute, of course, is the actual flow rate that the iDROSET measures, and that's measured as part of the balancing process. BTU per hour is the actual load, whether that's a heating load or a cooling load. Delta T is the temperature drop through the system from the supply to the return. Typically for most hydronic systems, that's calculated as 20 degrees. It could be 10, could be 30. But the average rule of thumb is about a 20-degree delta T. And finally, 500 is a constant. That's the heat carrying capacity of pure water. So what will happen in most commercial applications, and especially if it's a specified job, each heat emitter or cooling emitter or each fan coil or each chilled beam will have a specified flow rate that it needs to receive to maintain optimum operating efficiency and to keep the occupants comfortable. And that's all based again on the load. And if we don't supply enough flow, then we don't supply enough capacity, either heating or cooling, for that fan coil or whatever it is to do what it needs to do. Conversely, if we flow too much, if we just over pump that heat emitter, what'll happen is the delta T will get smaller. In other words, instead of a 20-degree delta T, we may have a 10-degree delta T or even a 5-degree delta T. And as that delta T shrinks, what happens is both chillers and ModCon boilers, modulating condensing boilers, become less efficient. Specifically with modulating condensing boilers, they really depend on the coolest water possible coming back in the return to keep them in condensing mode. So once we start over pumping, one of the big problems is going to be loss of efficiency. We also have the potential of having velocity noises in the piping system by over pumping. And plus the pump itself will consume more electricity pumping a higher GPM than it will a lower GPM. So we really need to balance, but the primary reason we're going to balance, aside of all those other reasons, is to ensure maximum comfort to the occupants inside that building. In a balanced system, what we're going to have, all the benefits I just described, we're going to have flow that is appropriate to each of the heat emitters or cooling fan coils. In this particular illustration, we're showing a kind of a conventional cast iron radiator, simply just two radiators. But really what we're looking to do is have flow rate that is appropriate into the design that's required for those emitters to perform, to keep the customers and the occupants comfortable and to maximize the energy efficiency of the system. The next slide will show you a little bit more about some of the complexities and the balancing process that's really required. This is perhaps a simplified a schematic, but it shows a couple of things going on here that I'd like to point out and describe in greater detail why we need to balance. So on this, you'll see we have a heat source on the left. We have a common system pump. You will see there are 4 risers going from left to right, and each one of those risers has 5 radiators. So as we look at each riser, the lowest radiator is the shortest path between the supply and the return line. The supply line being the red, the return line being the grayish color. So if we had no balancing valves on that vertical riser, the flow would flow mostly through the path of least resistance, which is going to be the bottom 1 or 2 radiators. And what will happen as we get toward the top, that top radiator, without the benefit of balancing, that radiator will be starved for flow, simply because of the longer pipe run, the greater pressure drop. The water is going to flow through the path of least resistance. So that top radiator gets starved. So as part of the balancing process, really what we're doing is we are artificially choking down the flow on those lower radiators to push flow up to the upper radiators. And as part of that balancing process, it's a sort of a simplified way of describing it, but basically what we want to end up with is equal flow or flow that's appropriate as designed for each one of those radiators. So the balancing becomes really not only important, but it can also be a time-consuming job, because every time you adjust one balancing valve, it changes the flow in another. Then we look at the actual vertical stacks themselves. If you see, there's also a balancing valve on the return going back on each stack, going back to the main return, going back to the boiler. If we only had the stack on the left, then we wouldn't have to worry about having that extra balancing valve on the return of the stack. But if we were to take a look at it, it's really the same situation that's happening with each vertical stack with the radiators. The vertical stack all the way on the right has the longest distance, the most piping. So it's going to have the greatest pressure drop. So if we don't balance not only radiator to radiator, but stack to stack, what'll end up happening is that stack all the way on the right, having the most amount of pipe and the greatest amount of pressure drop, is going to get starved for flow. So it's really, when we say balancing, it really is a balancing act to get all of these radiators and stacks properly tuned so that each heat emitter or radiator is getting the flow it needs to deliver the designed heating or cooling load. So in a brief kind of 30,000 foot view, that is what we're up against when we're balancing. And that is why it's important that we do this kind of a process to ensure that the system not only provides the comfort it was intended to provide, but also work in the most energy efficient way possible. So you may notice on this screen, if you're familiar with Watts products, all the way on the left, you'll see our CSM 61 circuit setter. That is a static balancing valve as well. And as you know, for those of you who have done balancing before, that requires the use of an external instrument known as a digital manometer, where you actually measure the flow rate or measure the pressure differential across that valve. And by knowing the CV value of the valve, CV basically meaning the flow rate that's required to create 1 psi of pressure drop. By measuring the flow, the pressure differential, the instrument can then calculate what the flow is through that circuit. That calculation is based on a couple of things. It's based, number one, on the CV value of the valve, and assuming that CV is perfectly correct and accurate. And then number two, it also depends on the accuracy of the actual instrument. They typically need to be recalibrated once every year or so. And then number three, sometimes there are calculations involved with variable orifice balancing valves, such as a CSM 61. There's a graph that needs to be used to input the correct information. So it's an estimation process. And really what that process means is that we are estimating the flow based on pressure drop. We're not actually measuring the flow directly, kind of inferring what it is based on the pressure drop going through that valve. All the way on the right, you'll see the Big Brother version of it. We offer these valves up to 8-inch in size for large commercial and industrial applications. You'll also see in that valve there are 2 test ports, and that valve will work the same way as a smaller valve. The balancing process will remain the same. And then finally in the middle, you'll see the subject of today's webinar, the iDROSET. The iDROSET was developed last year, over the last couple of years, by Watts Italy, and has been in the European market since last year. It's being well received. The technology in that valve, which we'll describe in greater detail, measures the flow directly. In other words, we are measuring the actual flow in the valve itself without the need for an external instrument. And we're going to talk a little bit more about the benefits of doing it that way. So of course, the applications for balancing installation is going to be heating, it's going to be cooling, geo, solar. We have commercial, small commercial jobs, large commercial jobs, industrial jobs, etc. So balancing here is a selection of balancing valve products. And again, the iDROSET in the center is going to be the subject of our conversation today. So question number one, go to it, guys. And ladies and gentlemen, good luck.
Looks like everyone is getting it right. The first person to respond was Scott. So Scott, congratulations, and thank you for everyone for your participation. Yeah, a lot of people got this, Jim. So
all right. Well, that's good. That either means the question was too easy or I explained too much. Well, congratulations, Scott. We have to tell you that, part of the deal is you have to share the beer that's in the cooler with us.
yes.
I'm sure you won't have a problem with that.
Of course.
Right. Thank you, Greg. We're gonna move on now to the rest of the presentation, and more questions coming up. So be ready. Okay, the ideal solution for static balancing. We're going to now talk about the subject matter of the day. So the challenges, as you saw in that one slide where we had the vertical stacks and the 5 radiators in each stack, As you start thinking about that, it's a complex, time-consuming setup and commissioning to go through, because again, once you balance one valve or one stack, you have to go back and balance the other. So basically, in a typical commissioning job using static balancing valves, you're typically running through anywhere from 3 to 5 times to get everything within specification or as close as you can possibly get it. So it is a very time-consuming job. You will also need people who are familiar with using the instrument, with doing the calculations, etc. And all of that between skilled labor and the time that it requires to actually balance the project correctly turns out to be expensive. So solution based on customer use. So the iDROSET's about a simple design that's easy to adjust, and offers quick operation. And we're going to talk about how we do that, how we accomplish that with the iDROSET product. So the iDROSET, we can look at it, and basically there are three functions in the basic construction of the valve. Number one, you'll notice there's a large dial on the top. That dial reads out the flow directly. In other words, you do not need an instrument to be able to tell what the flow is. It will indicate immediately as soon as the pump turns on. That needle will move, the black needle will move to indicate what the actual flow through that valve is. The red needle on the top is simply a needle you manually set to the design flow rate. So if the call out is for 2 GPMs per minute, you just manually set the red needle to 2 GPMs per minute, and then you'll set the iDROSET valve, adjust it to achieve the 2 GPM, so the black needle lines up with the red needle. The hand wheel on the outside is actually what you use to adjust the flow rate. That is mechanically attached to the valve mechanism inside the valve that will open and close and thus control the flow through the valve. The main body is made of a composite material that is obviously rust-proof, etc. And then we have brass end caps, which are what actually attach to the piping in the system. This particular model that's shown here is the European version with the British pipe thread connections. The North American version has standard female NPT piping connections. So what is it about the iDROSET that is going to help you get off the job more quickly? First of all, it's easy to read. You're not going to have to attach an instrument to see what the flow is. The flow will be live time, meaning as long as the pump is running, as long as there's flow through the system, the needle will be indicating it. It's obviously an easy to read gauge. It's easy to set. There's no tools involved. You just simply turn the hand wheel to get your required flow. On the photo, you'll see at about the 3 o'clock position on the blue handle, right by where it says closed, you'll see a small stainless steel set screw. Once you set the flow, you tighten that set screw and it locks the handle in place, so there can be no inadvertent changes to the flow rate. So no other devices are needed to read the flow rate, and precise calibration. We're going to talk about this. This is a really important aspect of the balancing process and also of the iDROSET valve. So to adjust, to set our flow, it's very simple. We adjust the hand wheel to the required flow rate, whatever that might be, and we can read the flow right off the dial. That's it. That's all there is to it. So we're going to show you a video coming up here, which kind of does a side-by-side of the iDROSET, balancing with the iDROSET versus balancing with a standard circuit setter using a digital manometer. You can imagine it's going to be quite a difference in the time taken. So precise reading without external instruments, easy to use, time saving. Another big aspect of the iDROSET, it has a very wide working window. What you'll see on the spec sheet, which I'll show you where you find those, is that it has a very wide range of flow rate. So you have a much wider working area as compared to a traditional circuit setter. The technology inside the valve allows it to work under this larger window than is normally associated with either a fixed orifice, variable orifice balancing valve.
Jim, we had a question come through. Does it come with PEX fittings?
Test fittings, meaning
PEX,
test ports.
PEX.
It does not. In this screen, that's actually a great question. And this slide that's up right now will partially answer, or will actually entirely answer the reason why it does not. Again, remember when you're using a digital manometer with a standard circuit setter, it is a calculation. You are estimating flow based on a pressure drop that is supposedly right on the money, perfect in terms of a CV rating of the valve. So at best, when you're using a standard circuit setter, you are estimating the flow. It's not a precise actual reading of the flow as you get with the iDROSET. The iDROSET reads the flow directly. It's a flow meter as opposed to taking a pressure differential reading and then calculating what the flow might be based on a CV number or the resistance inside the valve. To that point, these valves are manufactured in our factory in Italy. Every single valve, before it gets packed, goes on the test stand that you see right here. On the left side, you'll see the entire test stand with all calibrated instruments. And what we are doing is we're testing that valve at 4 points in its within its range. We're taking a reading at its lowest point. We're taking a reading at its highest point, in other words, its highest flow rate, and then 2 points in between. The standard it must meet on all 4 points is that must be within plus or minus 10% of the actual flow rate. Every single valve is tested. Every single valve leaves the factory certified that it's going to be plus or minus 10% of the actual reading on the needle. So you'll see the test setup there on the left. On the right is sort of a close-up of the screen. You'll see the happy face on there. The happy face means that valve test passed. And you'll see the 4 readouts there where the flow was taken and the valve passes, it gets packed up and out the door it goes. So plus or minus 10%. Now, where does that plus or minus 10% come from? Why is that a big deal? Next slide will describe it. The National Environmental Balancing Bureau produces the procedural and standards for testing, adjusting, and balancing environmental systems. This applies to both the air side because a typical system is going to be a fan coil with ductwork that's either getting chilled water from chillers circulating through it or heated water from boilers circulating through it. So the commercial system has 2 sides. It has the air side and it has what we'll call the wet side. And the NEBB standard here covers both the air side and the wet side. In regards to the wet side, to the hydronic side, section 9.4, second paragraph down, you'll see there's a couple of different methods that are appropriate for all hydronic systems, but you'll see in italics, regardless of the method, the objectives remain the same and the system will be considered balanced in accordance to NEBB procedural standards when, bullet point A, take a look at that, all measured hydronic flow quantities are plus or minus 10% of the design. So there it is. That's where it comes from. It's the standard that is used for balancing systems. Now, there might be some engineered systems that require a 5%. What we found in our testing, our own testing in North Andover with our samples is that over a tremendous range of the valve, we are well within the 10%. It's really only when you get down to the minimum flow rates of range in each valve size that we creep up toward that plus or minus 10%. But in the vast majority of the range of that valve, especially in the higher flow rates, we're well within 10%. So the bottom line is you can balance a system to plus or minus 5%, but most balancing contractors will push back on that to the specifying engineer because it is so time consuming to get to that level of accuracy. So the standard is 10%. And the iDROSET valve, as it comes out of the factory, is well within that plus or minus 10%. It is reading the flow directly. You are not calculating or estimating flow based on pressure drop. It actually reads the flow inside the valve. So that's where the plus or minus 10% comes from. So here are the sizes of the iDROSET. We are launching the valve with the half, 3/4, and 1 inch. You'll notice that we also have in the works the 1 1/4, 1.5 inch, and 2 inch. Based on our CSM circuit setter sales, the vast majority of sales are in the half and 3/4 inch. There's some on the 1 inch. Once we get into the larger sizes, at least with our standard circuit setters, we don't see as much unit volume with that. But the 1 1/4, 1.5 inch, and 2 inch will be coming. You will see the maximum temperatures, etc. You'll see the CV values for each one. And in the engineering sheet, which we're going to show you here in a little bit, where you find that, you will also see the specified range for each valve. So we always size a valve based on its flow rate range, not on tapping size. So that's something important to keep in mind. So
Jim, I'm just getting a couple questions that came through right now. I think that
sure.
a couple minutes ago, so it might be back a slide. Is it directional? Is there an arrow on it? And can you
Yes, it's directional, and there is an arrow on the back of the unit that shows which direction the flow is in. So yes, it is directional, and there is an arrow on the back of the unit, on the back of the valve to indicate the proper positioning.
And can you point out the set screw?
The set screw, if you look at this photo right now, if you look to the 3 o'clock on the blue dial, just outside on the black, you'll see it looks like chrome. It's actually stainless steel. You'll see a stainless steel set screw. Everybody see that there? It's on the at the 3 o'clock position on the hand wheel. That is the set screw. So once you set the valve to the proper flow rate, you tighten down that screw, it locks down the handle so it can't move. And that's right there on the right side. It kind of overlays the brass end cap. But it's on the right side, 3 o'clock to the blue ring.
Very good.
All right, on we go. Take a look. Take a look at the left side. We're balancing the flow. You ready? It's going to take a long time. There we are. We got it. That's it. We just set the flow with the iDROSET. Going on the right side is the guy with the standard circuit setter. Right, he's got to take the caps off the test ports. He's got to insert his probes. He's got to set up his manometer. Right, so this goes on for a while. I'm not going to make everyone watch this whole thing. I think the guy's kind of taking his time a little bit. This was filmed in Italy. You know, he's kind of taking his time setting this up, but it's pretty representative of what's required. He has flow rate going on. You know, you have to turn on the instrument. This particular case, it's actually a watch manometer that is calibrated for a specific model. So now you select a specific model, and you go through all this stuff on the digital manometer. He's kind of selecting which valve he's using, the size, et cetera, and then he starts adjusting the flow, right? And every time you adjust the flow, he has to go in and take a reading on his instrument. So he's doing this over and over, and every time he turns the valve, he actually has to take another reading and see where the flow is. And when he finally gets it to the point where it needs to be, he can finally say, okay, good, that valve is now set. Now, don't forget that when we adjust other valves in the system, the flow on this one's going to change. So he has to come back. He's not doing this just once. Might be doing it 2 times, 3 times. You might be doing as many as 5 times, depending on the complexity of the system. And how the piping is laid out. But this is the process that someone is basically going through when you're using a standard circuit setter with a digital manometer. I'm not going to make you watch the whole thing, but here's the bottom line. It took us about 13 seconds with the iDROSET to set the flow, to read it, and to set it. In this particular case, we're saying 2 minutes and 29 seconds. Yeah, he might have been able to get it done like in 2 minutes, but no mistake about it. Using a standard circuit setter with an external instrument is a very tedious and time-consuming process. This is where the iDROSET is going to save a ton of time on the job. We no longer have to go through this whole process as shown on the right side to estimate what the flow is. We can read the flow directly, turn the hand wheel, set the flow to where it needs to be, move on to the next one. Now, if you think about that, if you only have 1 or 2 valves in the system, not a big deal. But you think about that that system that we had on the previous slide where we had 4 stacks, each with 5 radiators. So there's 20 circuit setters there, and then we have one at the bottom of each stack, 24 of them, right? We're gonna have to go through and go through multiple times, recalibrate these. If we have to hook up a manometer every single time, even if you have 2 of them, you have 2 guys on a job, the amount of time taken to do that is amazing. It is an extremely long process, and this is the key advantage of the iDROSET, is that it speeds up that part of the balancing process tremendously. And this is where the value is for the balancing contractor.
Jim, we had a few questions come in. Actually, we have several, but I'm only going to try and knock out a few right now before we go to the next slide. Does the brass fittings meet the lead-free laws? If not, when can we expect it?
Great question. The current model is for hydronic systems only. In other words, heating and cooling systems. We have a lead-free version we expect to launch in early next year, probably Q1 of next year. That will have lead-free brass. Additionally, instead of straight female unions on each side, it'll actually have unions. So it'll be the standard Watts interface union, and we will have sweat tail pieces, threaded tail pieces, and press tail pieces available. So the lead-free model's coming. It's a great question, and we understand there's a tremendous opportunity for this product in hot water recirculation systems. It's going to be an absolute natural, great accessory for the IntelliStation systems. So the answer to the question is no, you can't use this one for potable water applications, but the lead-free version will be available in Q1 of next year.
Okay, next question. No systems are perfect out of the box after install. Sometimes there's air to dirt in the system. How does the valve deal with this?
Good question. So what our recommendation is that if this is a new system, totally new, once you're done doing your standard flushing procedures on that system, there should be no issues whatsoever. We do, however, advise that if you are retrofitting the iDROSET into an existing system that has a lot of ferrous components, most of the old systems do. They have steel pipe, they might have cast iron boilers, cast iron circulators and other components, etc. We still recommend flushing the system, but the best way to deal with that is to install one of our Y strainers upstream of the iDROSET to protect it from those older systems that probably have quite a bit of debris floating around in them, no matter how much you try to flush them. One of our Y strainers, like the 777, will do a good job of protecting the iDROSET from that.
Okay, next question. Since the flow rate is set according to what's required, is there a pressure drop range for each valve, or is it constant?
Yes, there is a pressure drop range. There is a CV value assigned to the valve. So with each valve, on our ES sheet, you will see there's a range of flow rates that is recommended for. One of the things that you'll notice on the ES sheet is that the low end of the flow rate is really low. And it goes down lower than most other valves, and has to do with the construction of the valve and the way the flow meter was constructed inside the valve. And the upper end of the flow rates are pretty much what you would expect. So that goes to that expanded window we were talking about in terms of being able to operate over a broader band of flow rates.
Okay, I'm just going to read off 2 more questions here, then I want to move on. But does the iDROSET include some sort of handle locking mechanism?
Yes, that's that the nut that we saw on the previous slide. See if I can go back to it. Right there. If you look at the iDROSET in the bottom right corner, you'll see that stainless steel Allen key screw at the 3 o'clock position coming in from the side. So once the valve is set, screwing that screw in, basically what it does is it locks the handle so that it cannot move inadvertently.
And are these available lead-free for use in domestic hot water recirculation?
Yes, as per the previous question, we will have those available in Q1 of next year, the lead-free version, and it'll be the same valve, except it'll be made with the lead-free alloy, and they will also have unions on each side as opposed to just a standard female pipe thread, and we will have tail pieces available for thread, sweat, and press on the lead-free version.
Very good. I think we're good to move on.
All right, here's the next question. Go at it.
Wow, people are on top of this. Very quick response. We have a winner. Andrew, you win a cooler.
All right, nice job, Andrew.
Very good.
All right, okay. Little heads up. Watch the next slide. Are you ready? Everyone ready? Another question.
Back to back. All right. Answers are various here. But the first person to get it correct was Chet. So congratulations, Chet.
All right, thank you, Chet. So this one was, I wrote these questions, by the way, so you can blame me. This one was, I worded this in a way that you really had to kind of read it because I figured everyone would like really be jumping on the answers quick, and I bet you got a lot of D's, didn't you? A lot of all the above.
Yes, a lot of D's.
Yeah, well, see, I kind of set them up for that, right? So there's no need to refer to system design specifications. That's not true. We need to know what the required flow rate is for each heat emitter for each balancing valve so that we select the correct balancing valve. Balancing valves are selected not on their line size, in other words, their tapping size. They are selected by the flow rate that they must handle. So you select a valve based on that. There's no need to properly size the valve. Well, that kind of goes into what I just described. No, the valve must be sized correctly based on the flow rate. So you're going to select the valve based on the flow rate window that it covers in comparison to the actual design of flow rate. C, there's no need to use an external instrument to read and set the flow. That's it. There's the answer. That's what the iDROSET's all about. It's taking that whole time-consuming process of using the external instrument, putting the probes in, making all the adjustments, et cetera, et cetera. So that's what that one's all about. So good job, everybody. We'll move on. We're getting close here to the end, and we'll get this wrapped up. We'll talk a little bit to the technical features, talk a little bit about how the iDROSET works. So basically, it regulates, meaning that we have a valve, a ball valve in there that is directly mechanically controlled by the blue handle. We read the flow rate. The flow rate is read. The gauge itself there's no water flowing through it, and it's not mechanically connected to the valve. Rather, inside the valve in that upper chamber where we're reading the flow, there's a magnet, and the magnet actually moves the valve, the needle in the gauge. So there's no, one of the questions we had, well, what happens if, the gauge fills with water? It's not connected. It's not in the water path. The needle is moved by that magnet. And it measures, right? We're measuring the flow rate. For any of the more, people, technical people who are familiar with balancing valves, you're going to notice a Venturi in there. You're also going to notice a check valve, and this is a patented design that uses a Venturi and then uses this check valve, which is not a conventional check valve. It's not going to prevent backwards flow, but rather it's a valve that helps improve the accuracy at the low range of the reading. But it's essentially a fixed orifice valve that's working on a Venturi, but it also is sort of like a variable orifice in that valve mechanism, that spring check valve mechanism on the right is going to move depending on the flow rate. So it's, if someone asks, well, is it a variable orifice or a fixed orifice? It's kind of both. It's a unique design That's going to be measuring the flow directly and give you the readout on the gauge. So that's sort of what the inside of the valve looks like, and fundamentally what it's doing. Um, Again, we just kind of a little more on the from the last slide. The Venturi is going to measure the actual flow rate using a Venturi method. The ball valve regulates the flow, and then we have a gauge that instantly displays the flow over its entire range to plus or minus 10% accuracy, and that is very, very conservative on that 10% accuracy. Our own in-house testing shows the accuracy to be considerably more than that. So here are the flow rates of the various valves. You'll see on the right-hand side, the half-inch is good from 0.15 to 3 GPM. So basically, if we use 20 degrees as a delta T, that's basically 1,500 BTUs to 3,000 BTUs. So, well, actually, no, that's 150 BTUs to 30,000 BTUs. I'm sorry, 1,500 BTUs to 30,000 BTUs. Notice the half and a 3/4 inch are really the same. It's because the internals are really exactly the same between the two. The advantage here is that we can use a half-inch valve where normally a 3/4 might be required. The 1 inch goes from 2,000 to 70,000 BTUs. And you can see the range for the large valves. We go all the way up to 44,000 BTUs on the top end on the 2-inch valve, and so that it's a pretty impressive. Actually, it's 440,000 BTUs, 17,000 to 440. On the left side, we can see the ratio. Variable orifice is typically 14:1. Fixed is usually 5:1. The iDROSET 25:1. So we have some really significantly wider operating window. And this is just another screen that shows another graphic that shows the range that it will accept compared to other kinds of valves on the market. So in conclusion, the iDROSET's going to make your job easier. It's easy to read the flow rate, right? There's no tiny bead to look for inside of a sight glass. There's no sight glass to become obscured, right? Some of the other products on the market, they're not that easy to read. Real-time checking. That valve, the gauge is going to indicate the flow as whenever the pump is on. There is no bypass circuit to actuate. There's no ring to pull in order to be able to read what the actual flow is. Large hand wheel makes the changes easy, right? You're not going to need a wrench. You're not going to need anything, a screwdriver or anything else to be able to actually change the flow. You can just read it, turn the wheel, and set the flow for exactly what you need. Patent pending technology for precise calibration, again, plus or minus 10% is the worst case scenario. It's actually better than that throughout most of its range. And as you can probably see by now, if you're used to working with standard circuit setters, it's a time-saving process. It's going to save you a lot of time on a job and get you in and out a lot more quickly than using a standard circuit setter. Last question. Okay, have at it.
Yes, everyone's getting this one correct. But the first person was Clement.
All right, good deal.
Congratulations. That was the final question.
So what I want to know is we gave away four of these coolers, right? So how many bottles of beer does that represent?
50.
You said we get 50
bottles?
Yeah, how many bottles of beer does that represent, Greg?
50 cans. I can't speak to bottles.
Okay, 50 cans. Wow. So, 50 cans times 4, a couple hundred cans of beer. Sounds like there's going to be some partying going on. Well, congratulations, everyone. This is a really cool, pretty cool prize. So we'll get this wrapped up now. Again, we thank everyone for being here and for taking some time to join us. We'll get this wrapped up now. On the Watts website, you can go and in the search box, if you just want to do it really quick, in the search box, you type in iDROSET. and it will bring you to the landing page for the iDROSET that is shown in the upper left. From there, you can then download, you'll see to the left of to the right of the arrow, new generation in balancing. That is the sales flyer. You will also see then next to that, the ES sheet. The ES sheet is going to have all the specifications, the flow rates, etc. for each size. And you'll also be able to download the installation instructions that come with the iDROSET. And then finally at the bottom, you're going to see a video. When you get to that page, a video is really, really well done. Really well done. I would really recommend that you visit the website and take a look at the video. It gives a really nice animation of how the valve works. Well worth a look. Also, on our Watts Works learning program, if you are subscribed and participating in that, you'll see that we have 3 modules for balancing in the iDROSET and what each one of those are worth in terms of points earned. So that is on our learning program for those of you who are using it. That is there, ready to go. And this wraps it up. I'm going to hand it back to Greg, who I'm going to allow to take care of the last couple of slides.
Yes, thank you, Jim. So we did have several questions come in, so appreciate all the engagement from you guys. The next 12 minutes or so, we'll try to do our best to knock these out.
Okay.
But first one here, what is the internal mechanism, a ball, SS ball? I don't know if that goes back to those 2 other questions.
Yes, it's a ball valve. It's a stainless steel ball valve.
Okay. Is there a time frame for stainless steel bodies?
Not at this time. So this is really the iDROSET currently is intended for your typical hydronic system, which is going to be water. It's going to be a water propylene glycol mix, and then with whatever additives or treatments are typically used in hydronic systems. At this point in time, we do not have anything for a stainless steel version that would be suitable for chemicals or any liquid that'd be aggressive to brass. So it's all basically hydronic, heating or cooling, and in Q1 of next year, potable water for recirculation systems.
Are there any minimum upstream and downstream straight pipe diameter required?
There is not.
Can you explain the overall benefit of iDROSET over the circuit solver balancing unit?
So that's a great question. The circuit solver is used in potable hot water recirculation systems. And if you kind of think about that one graphic that I had up with the radiators and the stacks, you have a similar situation when you have parallel return lines or recirculation lines in a domestic water distribution system. But there is a key difference, and it's a big difference. In a hydronic system, we must create and supply the flow rate required to cover the heating or cooling load. Those flow rates are directly associated and related to that formula, GPM equals heating load over 500 times delta T. In a hot water recirculation system, there is no load per se. The only real load on that system is going to be the heat loss through the actual piping, which is minimal. So as a result, the flow rates that are associated with a hot water recirculation system are very, very small compared to the flow rates seen in a hydronic heating or cooling system. The circuit solver is temperature based, and it allows each parallel circuit to reach the same temperature on recirculation, which works well in that regard. The problem becomes, for example, with the IntelliStation. For those of you who are familiar with the IntelliStation every 24 hours goes through what's called a sterilization cycle. And basically our return temperature on a hot water recirc might be, for conversation's sake, might be about 140 degrees, might be 130 degrees, somewhere in that range. depending on how the system is set up. The IntelliStation, once every 24 hours, looks to bring the return temperature right at the pump going into the water heater up to over 160 degrees. And the reason for this is that Legionella dies really, really fast when you get the water that hot. And one of the problems becomes is that with the with a temperature actuated valve, number one, you're limited to the temperature that you selected for that. And that number two, you have to use a valve that has a bypass that will allow that hotter water to go through. So when you're using it in a system like IntelliStation, it becomes a little more difficult to use and definitely has some big drawbacks. The iDROSET does not have any of those drawbacks. You're going to simply set the valve so that you have proper return rate on each one, and that it's the temperature is balanced between all of your various return legs. And then when that temperature kicks up to 168, not going to make any difference. You're going to get the same flow at 168 or 165 that you'll get at 120 or 130, whatever you have your recirc line set up for. So that's the main advantage of the iDROSET, is that it's not going to interfere, number one, or compromise the sanitization cycle, and number two, if for some reason you decide you have to change the return temperature on the system with those temperature actuated valves, you actually have to change the valve because they come set for one temperature.
Okay, and can you explain the 25 to 1 turn down? Does this mean that there is a gear that turns the ball valve that's inside?
The turn down ratio, what we're referring to is the range of accuracy on the reading. And that's, if you recall the slide with the Venturi showing the kind of the internal workings of the valve. We had the Venturi mechanism. We had that kind of that floating check valve. So the turn down ratio doesn't really refer to the actual ball valve. And by the way, that ball valve will serve as a positive shutoff, something I failed to mention before, but this can also serve as an isolation valve. There's no need to have an additional ball valve upstream or downstream to be able to effectively isolate a heat emitter or fan coil. So the turn down ratio has to do with the internal flow measuring mechanism of the valve, and not so much the actual ball valve or shutoff capability.
How does the flow meter read the flow?
Well, I guess that's sort of like proprietary information, but basically it's reading it through the Venturi. It is reading a pressure drop, but it is a direct reading. In other words, there's no interpolation via software. There's no interpolation based on what the CV of the valve might be. CV, again, is a designation given to the valve by the manufacturer that represents the flow rate at which 1 PSI pressure drop occurs. So let me just expand on that a little bit. Let's say the CV is 3, right? That would mean at 3 GPM, the pressure drop would be 1 PSI or 2.34 feet of head. So if the CV is not actually 3, let's say due to the way the valves put together, tolerances stack up, etc., the actual CV is 3.2, right? But you're still basing your calculation on 3. That's the number you're going to be putting into your digital manometer, because it all starts with what the expected pressure drop is in the valve. So you can end up with a CV that's not quite right, and then you could also end up with a meter that's not properly calibrated or has fallen out of calibration, unknowns to the user. And then you might also have some calculations involved that the user has to do in terms of using the actual instrument to attain the correct flow rate. All that's taken out of the equation with the iDROSET. It's reading it direct. It is a direct reading, not a reading based on a CV number of a valve that then is interpreted with an external instrument. That's why we call it a direct reading.
Jim, can you advance it to the next slide? I just want to make sure people can see our emails. I'm going to do my best to get through the next few questions here, and then we can wrap it up.
Okay.
Another question came through. Can the orientation of the gauge face be adjusted?
No, the gauge orientation is set, and it has to do with the construction of the valve and keeping its outer dimensions as compact as possible, and also with positioning in relation to that magnet. Remember the cutaway diagram, we have a magnet. The magnet itself kind of looks like a cylindrical plug that floats in that upper chamber. And as the flow rate changes, that magnet moves from side to side. And as the magnet moves, it pulls the needle along with it. So the gauge itself is, you cannot change the orientation of the gauge. You can, however, put the iDROSET in any position you want. You can gauge up, gauge facing down, gauge facing to the side. You can rotate the valve along the axis of the line any way you want, and it's not going to impact the operation of the valve. You would just I would say you would set the valve up in a real application in a way that's easiest for someone to read. And a lot of times these may end up over a suspended ceiling, so you may want the gauge facing down. In that regard, you can orient the iDROSET any way you want in relation to the axis of the actual line it's installed in.
Okay, if the gauge fails, is it replaceable, or do you need to replace the entire unit?
At this point, I am unaware of replacement parts. That gauge is really kind of built into the valve. There's not a lot inside that valve inside that gauge that can fail. I would say probably the chances of that happening are remote, but at this point in time, there's nothing available for replacement of any parts or field repair kits. Moving forward, that might turn out to be the case, but the valve comes fully assembled, fully tested from the factory. So at this point, the answer is no, the gauge by itself is not replaceable.
Okay, the face of the units, will they show GPM or LPM?
Great question. They will show GPM. So remember at the beginning of the presentation, I said this was a product that was developed in Europe for the European market. It's been on the market there since last year. In Europe, they use British pipe thread. That's why you kind of sort of like those union style nuts on there. The British pipe thread is a straight thread. It seals on the end of the pipe as opposed to a national pipe thread that actually seals on the threads. And their gauge has a liter per hour scale. So the changes that were made for the North American market is that we have a gallon per minute scale on the gauge. And the gauge itself is the same. It's just the actual, it's like the actual sticker that goes on the gauge that is in GPM. And then the other change that was made, obviously, is that we went from the British pipe thread connections to female MPT connections for the leaded version, and for the lead-free version, they will be unions on each side.
Are 10,000 LS or LM the max flow?
Max flow, you'll see in the ES sheet is rated in GPMs. So the 2-inch valve, for example, goes up to 44 GPM. So if I'm doing the math right in my head, that's 440,000 BTUs. The 1-inch valve, I'm just pulling the ones I remember. The top range for the 1-inch valve is 7 GPM, so that's 70,000 BTUs. So that's how you would determine the correct valve for the application. And again, that's going to be based on the formula that we looked at the beginning of the presentation, and the specifying engineer's specification for how many BTUs that heat emitter or fan coil needs to supply. If it's not an engineered job, then it's part of the heat loss calculation in terms of sizing fan coils. You would size the fan coil to the load. Once you know what the load is, you select the appropriate range of valve, the correct valve based on its range to be able to balance that fan coil.
And can it be installed horizontal, vertical up, and vertical down?
Yes, it can.
Does the valve come with a balancing sheet per valve or commissioning purposes, say for reports to engineers? Or
That is go ahead.
Or a sheet to fill out for all installed valves?
Yeah, that's a great question. Part of the balancing process is a commissioning report where the balancing contractor has to verify that each valve was actually set. That process, as we know, includes using the digital manometer, doing the whole adjustment, and then the commission report basically, it's a checkbox. Yep, it's balanced. The checkbox for the iDROSET is you set the valve to the appropriate flow rate. That would be the difference between the two, is that when you're doing the calculations and taking a reading off of a digital manometer and then saying, okay, good, it's set, versus the iDROSET, you're just taking the reading off the gauge.
Any plans on having a Bluetooth or Wi-Fi readout of flow rate?
That is a distinct possibility. IoT devices are a big initiative under the Watts umbrella. They are currently working on such a model in Europe, and I suspect it will only be a matter of time before that product comes to market and will be available here. So no time frame, but yes, that kind of product is very much in the works.
To clarify, these are able to be used in domestic systems, or is that model is next year?
The potable systems, hot water recirculation, lead-free models are next year. Q1. Q1 should be it. We're hoping for like a February or March launch for the LF version.
And what does CSD stand for?
All right, so our CSM series, CSM-61, stands for Circuit Setter Manual. CSD stands for Circuit Setter Dial.
Is the valve easy to be cleaned or serviced? Are there replacement parts for internal components?
There are no internal replacement parts right now. But again, if it's suspect that the system has debris, if it's an old retrofit system, we do recommend in the installation instructions that for retrofit applications that a something like the Watt 777 Y strainer be used upstream of the valve.
Is there an option for the material of the gauge face?
No, there is not.
EPD code?
They are on the ES sheet, which can be downloaded on the website. They're right on the ES sheet itself.
Final two questions here. In case we have systems with variable flow, I would like to know that the use of the iDROSET CSD is appropriate. That's more of a statement. This next question, does the set screw still allow the valve to be closed? Should it need to be used as a shutoff, still allow it to return to the balanced position?
Yeah, the balanced position, the set screw just locks the handle, right? And the handle is what turns the valve, right? Turns the ball inside the valve. So once the handle's locked, the ball's not going to turn. But if you need to isolate the system, you're going to have the red pointer, which is set to what your flow rate needs to be. So you can close the valve, and then when you reopen the valve and reestablish flow through the heat emitter, you're just going to adjust the valve to the proper flow rate, and you're probably going to end up right in the exact same spot at where it was before.
Very good. So that does it for the questions. As you can see, our email's up on the screen. Any logistical type questions, you can direct them towards me. Any more topic related question, you can send them to Jim. And Jim, if you can just advance to the last slide here, we'll wrap up. I just want to let you guys know that we'll be sending a follow-up email with a chance to test drive iDROSET for free. You just need to be one of the first 3 people to sign up and agree to work with us on a case study. And we'll send you the right amount of iDROSETs that make sense for you to try out in your facility. Then afterwards, we'll follow up with you and ask about your experience, and we'll just go from there. So keep your eye open for that email. That includes all the details around the giveaway. So that wraps things up for today. Thank you very much, Jim, for presenting and going through all those questions. It was great to see everyone participating there. And with all the quiz questions, congratulations to all the winners, and good luck to those who want to participate in the test drive giveaway. This has been great. So thank you all very much, and enjoy the rest of your week.
Thank you all for attending. We appreciate your time.